Hello everyone, and welcome again to Nettle, the best platform around for distance learning in business, finance, economics, and much more. Please don't forget to subscribe to our channel and click that bell notification button below so that you never miss fresh videos and tutorials you might be interested in. Many thanks to our current Patreon supporters and YouTube members for making this video possible, and we'd also greatly appreciate if you consider supporting us as well. So please check the link in the description or click the join button below for more details. My name is Sava, and today we're investigating a key concept in probability theory and statistics, that is binomial approximations, or approximation functions that can proxy the binomial distribution we have covered in one of our previous videos quite effectively when your number of trials is sufficiently large. And let's start with our old example from the last video. A reminder, or for those who haven't watched it, we investigated the following case. Let's say that we've got 20 students who take a CFA exam or an ACCA exam, some chartered exam that is very competitive. And the probability of success, the probability of passing an exam for every single individual student are independent of each other and is equal to 0.7, 70%. Which means that the probability of failure, the probability that a student would unfortunately not pass the exam, is 1 minus p, the probability of success. And then we have investigated how we can model the probability that a certain number of students succeed using a binomial distribution that is expressible as n choose k times the probability of individual success raised to the power of the number of individual successes times the probability of individual failure raised to the power of such failures. And it can be quite intuitively understood mathematically as this bit over here is the probability that k particular students pass the exam and n minus k other students fail, whereas the n choose k tells us how many different combinations of such occurrences exist. And this binomial distribution function, the probability mass function that tells us the probability of k successes out of n, can be expressed the following way in terms of the factorial functions. And it is very efficient and very implementable for small n. However, for large n, we can encounter a problem. But first of all, let's remind ourselves how to implement the binomial probability mass function in Excel using the factorial. We first need to take the factorial of our number of trials n, lock in the row. Then we need to divide it by the product of two factorials. First, a factorial of n minus k, n stays locked, whereas k doesn't, as that's the number of successes we seek to vary, times the factorial of k itself, factorial of cell A9 in this particular case. And then we just need to multiply by the probability of individual success, row locked, raised to the power of such successes, k not locked, times the probability of individual failure, q locked, to the power of the number of such failures, that is n, row locked, minus k, row not locked. We can see that everything apart from k is locked, as it stays the same no matter how many successes are we interested in for this particular case. And we can enforce this formula and bottom click it down to easily verify that, first of all, the sum is 100%, meaning that we have taken into account all possible scenarios, and the most likely outcome is 14 passes. And that is not a coincidence, as the most likely and average outcome, the average number of passes and most likely number of passes, is actually NP, which is number of trials times the probability of success. 14 students on average would pass the exam, or for some other implementation, 14 shots would reach the target, and so on and so forth. There are so many different applications and interpretations of the binomial function. Also, what we have investigated during our last video and showed it using some simple calculations is that the variance of the binomial distribution is NPQ, basically number of trials times the probability of success times the probability of failure. And here we'll see that the variance of the number of students who pass the exam out of 20 is 4.2, and that gives a standard deviation or standard error of slightly higher than 2, meaning that the number would on average fluctuate between as low as 12 and as many as 16. What is the reason for why such a process, such a calculation is not always possible, is that the factorial function does explode quite fast. And if we try to calculate the factorial of even something quite small in terms of the input, so let's assume that we want to calculate the factorial of 170. 170 is a pretty small number, all things considered. Humans can visualize 170 items, at least to some extent. But if we plug it into the factorial function, we get back a number that is larger than the number of atoms in the observable universe. This is the scientific notation, and that basically means that the number is approximately equal to 7 times 10 to the power of 306. That is a number that no one can really make sense of. And what is even more surprising is that when we try and calculate the factorial of 171, Excel refuses to deal with such a large number as it doesn't have enough capacity to do that. Meaning that for numerical applications, the binomial function, the closed form solution we obtained, is not really feasible computationally for a large value of n, for a large number of trials. And that is very unfortunate. However, there are approximations that do not require you to calculate n factorial, and that, accidentally, work very well when n is large. So when we need it, it is there for us. So let's investigate the two approximations that are most frequently used. The one that we have got here, slightly below the original binomial probability mass function, is the so-called Poisson probability mass function, or the Poisson distribution function. And that has as its input, obviously, the number of successes that we seek, k, and only one parameter, lambda, instead of n, p, and q, three parameters that we've got for our binomial distribution function. Lambda here can be parameterized as n times p, so the average number of successes in the binomial distribution. The Poisson distribution is most frequently applied outside of the context of approximating the binomial when we want to model the number of occurrences of a particular event in a given time period when the intervals between such events are random and independent. For example, it is often used to model the number of goals scored in a competitive football match, or, for example, the number of calls a particular call center receives. In our case, we're using that to approximate the binomial distribution, so we're not necessarily interested in the application for number of same events occurring during a certain period of time. One of the most natural science related applications of Poisson distribution is actually to model the frequency of earthquakes. How many earthquakes would happen in a particular region in a particular time period. But here we're interested in plugging in our NP value, which is the lambda for the Poisson, and refer to the different values of k, which is the number of successes, and compare how well does Poisson proxy our binomial, our true probability mass function for our parameter values. So let's implement the Poisson probability mass function. We input lambda and lock the row, raise lambda to the power of k, number of successes, multiplied by the exponent, e to the power of negative lambda, and here lambda needs to be locked as well, and finally divide all of it by the factorial of k. And having applied this function, we can bottom click it all the way down and see that even graphically there is a very noticeable divergence of the Poisson probability mass function and the true binomial, probability mass function in orange and blue respectively. And this is unsurprising, given that Poisson performs the best when n is large and the probability of success is small, so we can actually verify it by setting the probability of success to something quite small, for example 0.05, and then Poisson and the binomial functions would be actually much closer. However, for our case, when p is 0.7, it is not the case at all. The deviation is substantial, and it would not allow us to use such an approximation for this particular use case. What to use in this case? Well, for n large and p not small, the go-to approximation is the so-called Laplace approximation. And you should not confuse it with the Laplace distribution, which we have covered in one of our unrelated videos, but rather it is a derivation that shows that as n is large, the binomial probability mass function can actually be approximated quite well with a normal probability density function. So our binomial distribution does tend to the normal distribution as n grows large. And that is one of the use cases of the central limit theorem. And as the parameters of our Laplace approximation with the normal distribution, we can use np for the mean and npq for the variance, meaning that our standard deviation would be the square root of npq. And here we can use the closed form solution for the probability density function of the normal distribution to represent our Laplace approximation of the binomial. So here we input 1 divided by the square root of 2 times pi times the variance, so npq, sigma squared for our normal approximation, times the exponent, e to the power of, negative k, number of successes, minus the expected number of successes, the average number of successes, and p, or mu, in this parameterization, that we need to lock row-wise as usual, squared divided by 2 times sigma squared, so 2 times variance, or 2 times npq. And here, again, variance needs to be locked as well. And then we close the appropriate number of parentheses and enforce the probability density function of the normal distribution, or the Laplace probability mass function. And as we bottom right click it all the way down, we can first see that just like for the Poisson distribution, our sum of all probability mass functions does deviate from 1, meaning that it's not a perfect approximation. It is off by some factor. Even this particular number gives us this idea. However, it does approximate our binomial probability mass function quite well. And we can see it from the graph as well. The gray line, the Laplace probability mass function, does almost perfectly mimic the binomial probability mass function in blue. And as we have discussed previously, for small values of p, the situation is the reverse. Here, our Laplace probability mass function is way off, whereas Poisson does a pretty good job at mimicking the real binomial PMF. And that's why you use Poisson when n is large and p is small, and you use Laplace when n is large and p is not small. And finally, we can calculate and compare the graphs for the cumulative distribution functions, and there is nothing easier than that. For the very first input, for 0 number of successes, we just refer to the respective PMFs, as per the definition of CDF, there cannot be any lower number of successes than 0. And then we just add up, as per the definition, it's the cumulative function, the respective values of the PMFs. And then, enforcing these formulas throughout, we'll also get a glimpse of the goodness of fit for our approximations in terms of cumulative distribution functions. Here, we verify that for large p, Laplace is doing a much better job, whereas for small p, like 0.05, it is the other way around. Binomial and Poisson are almost identical, whereas Laplace is off by a wide margin. And that's all there is for Poisson and Laplace approximations of the binomial distribution and their applications in Excel. Please leave a like on this video if you found it helpful. In the comments below, I'm eager to see any further suggestions for videos in business, finance, or economics you would like me to record. And please don't forget to subscribe to our channel or consider supporting us on Patreon. Thank you very much, and stay tuned.